Hi and welcome back. So in this video we're going to be working on this problem. So if you want to pause the video, pretty much I'll just state the problem now. We're going to take a look at this. So 4.04 grams of H2 of hydrogen gas is mixed with 64.00 grams of O2 gas in a 15-liter sealed flask, and after a reaction forming water takes place, what is the total pressure inside the flask if the temperature is maintained at 125 degrees Celsius? So this is our information here. And for the purposes of this video, I'm just going to tell you what the molar mass of hydrogen that we are going to consider. They'll make things work out a bit better. And you know, if you round to three significant figures, the molar mass of hydrogen molar mass is going to be 1.01 grams per mole, and also the molar mass for oxygen, just the single atom, is going to be 16.00 grams per mole. So anyway, this is pretty much the problem. So if you want to pause the video and try to figure out on your own, otherwise I'm just going to start getting into it. So if we take a look at this, so we have 4.04 grams of H2 gas. So if we wanted to figure out, and the first step that we're going to take is we're going to figure out how many moles of hydrogen and how many moles of oxygen we have. So how many grams per mole of the molecular gas do we have? And keep in mind, we're not really concerned with how many atoms we have. We want to know how many little particles of gas we have floating around. And remember that there are going to be 2 hydrogen atoms in each of those little molecules of gas. So in order to figure out how many moles of it we have, we're going to take our mass in grams. So we've got 4.04 grams of H2. And what is our molar mass going to be? Well, it's going to be 2 times the molar mass of hydrogen, right? Because we've got 2 hydrogen atoms in each molecule. So it's going to be 2.02 grams per 1 mole. And we don't even need the calculator to do this. You should hopefully you can see that we are going to have 2 moles of H2 gas. And so now let's figure out how many moles of oxygen we have. Similarly, we know that the molar mass of 1 atom of oxygen is 16, but we've got 2 atoms of oxygen in each molecule of the gas. So in order to figure out how many moles of the gas molecules that we have, we're going to take our mass. So we take 64.00 grams of O2 and multiply that by twice our molar mass for the atom of oxygen, right? Because we have 2 oxygen atoms in each molecule of gas. So this is going to be 32.00 grams per 1 mole of O2. And so also you can probably see that we're going to take 64 and divide it by 32, and we're also going to have 2 moles of O2 gas. And now at this point, probably the most helpful thing, because remember we have a reaction where we say after a reaction forming water. So we know that we are going to have a reaction where we are reacting, let me just write this down, we are going to be reacting H2 gas plus O2 gas, and we are going to be forming H2O gas. And the thing that you should hopefully realize about this equation right now is that it isn't balanced, right? It is balanced in terms of hydrogen, but we've got 2 atoms of oxygen on our left side of the equation, and we only have 1 on the right. So we are going to have to balance this equation. So probably we know that we're at least going to have to stick a 2 in front of it to be our coefficient in front of our water, and then that gives us 2 oxygen on the right side and also 2 oxygen on the left. But now we've got 4 hydrogen on our right side, and so we want to have 4 hydrogen over here. So if we just go ahead and stick a 2 right there, then this reaction is now balanced. But maybe in balancing that, you see a bit of a problem with how many moles of each of the gas that we have, because we've got 2 moles of hydrogen and 2 moles of oxygen. So in order for this reaction, in order for us not to have a limiting reactant in this reaction, we would have needed twice as much hydrogen. So if we had 2 moles of H2 gas and only 1 mole of O2 gas, then we wouldn't have had any limiting reactant, and we would have been able to say, okay, well, we started out with 2 moles of H2 and only 1 mole of O2, and that got, I guess you could say, it got reduced down to only 2 moles of gas in that reaction. But that isn't the case. You can see that based on our supplies, based on how we have 2 moles of H2 and 2 moles of O2, we are going to have a limiting reactant. We are going to have more of something left over. So let's try to figure out what would that be, right? So if we put 2 moles, if we use up all 2 moles of our H2 gas in this reaction. So if we put in 2 moles, we're going to form 2 moles of water. And how many moles of oxygen are we going to use? Well, we're only going to use 1 mole, right? So I can even, well, I don't need to write the coefficient in there, but we can see, hopefully you can see that we start out with 2 moles. So we're going to put 2 moles of H2 gas into this equation, into this reaction. And we can only put 1 mole of oxygen. We can only put 1 mole of oxygen. And then we're going to get out 2 moles of our gas. And remember that pretty much what we're doing, so we're taking 3 moles of gas. So we started out in this reaction where we had 4 moles of gas bouncing around inside this flask, and now we're taking 3 of those moles and we're reducing it down to only 2. Okay, so hopefully you can see that. So we're reducing. So we started out with 4 moles. After the reaction happens, 3 of those moles get reduced down to 2, and then we're also going to have 1 mole of oxygen left over. So you can think about it, maybe think about it this way. I hope I'm not confusing you with how I'm doing this, but you can think about saying that all of our hydrogen is going to take place in this reaction forming water. But only half of our oxygen is going to take place in this reaction. So therefore, in this reaction, we're going to form 2 moles of water, but we're also going to have 1 mole left over of oxygen. So therefore, after this reaction takes place, and we want to know what the total pressure is inside of our flask after the reaction, we want to know what the total pressure is. We need to know how many moles of gas we have after the reaction. So you can think that all 2 moles of our hydrogen gets used up, and then half of our oxygen gets used up. So we form, from 2 moles of hydrogen and 1 mole of oxygen, we form 2 moles of water, and then we're going to add to that our 1 mole of oxygen, which didn't react. So all in all, after our reaction, we are going to have 3 moles of gas particles floating around inside of our container. So now, hopefully you can see that we're now at a point where we can plug this into our ideal gas equation. So I'll just write this down. We have PV is equal to nRT. And we are going to be solving for pressure, so I'll just go ahead and solve for pressure. So P is equal to nRT over V. And we can see, let's just make sure that we have all the information we need. Do we know what the temperature is? And yes, we do. We know that the temperature is going to be maintained at 125 degrees Celsius. We know what R is. R is going to be our ideal gas constant. We've just figured out what N is going to be. So even though we started with 4 moles of gas bumping around, after this reaction takes place, we're going to be left with 3 moles of gas, 2 of which are going to be water and 1 is going to be oxygen. But I guess we're not trying to figure out what the partial pressure is for each of these gases. We just want to know what the total pressure is going to be inside the flask. So we are going to have 3 moles of gas inside the flask. So that's our N. And we also know V. We know that we are operating within a 15.0 liter sealed flask. So now we can just start plugging in numbers. So I'm just going to start and say that we have 3 moles, that's our number for N, multiplied by 0.08206. And I'm going to leave, again, if you want to see what the units are on this, maybe look further back in the playlist, but to save space, I'll leave the units off. And then we have 125 degrees Celsius, which we have to convert to Kelvin. And I'm actually going to get my calculator to do that. So we have 125 plus 273. And that's going to give us 398. I should have been able to figure that out. That's going to give us 398 Kelvin. And we're dividing all of that. We're dividing all of that by our volume, by our 15.0 liters. And what's this going to give us? So I'll get the calculator again. So we have 3 times 0.08206 times 398 divided by 15. And that's going to give us 6.53 atmospheres. And I think, yeah, we have 3 significant figures. So this is going to give us 6.53 atmospheres. That's going to be the pressure inside our 15-liter sealed flask. And that's our final answer for this problem. Hopefully you found this useful, and in the next videos I'll just keep doing examples. So thanks for watching, and I'll see you soon.